Hey everyone, welcome back, and today let's solve LeetCode problem 2094 titled Finding 3-Digit Even Numbers. So we're given an integer array digits where each element is a digit. Now the array may contain duplicates, which is a very important factor to consider when solving this problem. Now we need to find all of the unique integers that follow the given requirements, where the integer consists of the concatenation of 3 elements from the digit in any arbitrary order, really just meaning that it's built from 3 different elements in the input array. The integer should also not have any leading zeros, and it must be even, meaning it's divisible by 2. Right? So, for example, if the given digits input array was 1, 2, 3, the integers 1, 3, 2 and 3, 1, 2 would follow the requirements of being, or rather having a length of 3, meaning it has 3 different digits in the actual integer, and every digit in both of these integers are actually present in the input array digits. Now we want to return a sorted array of the unique integers, basically meaning in ascending order from least, or rather smallest to greatest. So in example 1, we have our input array digits to be 2, 1, 3, 0. In this case, there's a lot of different possible input arrays that could be formed from 3 different unique digits in the input array digits to still have that requirement of being even, not having any leading zeros, and kind of having that concatenation of 3 requirement. In this case, all of them are 1, 0, 2, 1, 2, 0, and so on and so forth. Notice how one common pattern between all of these integers is that they're all formed from digits that all belong in the input array digits. They're all a length of 3, and they're all even. And they also don't have any leading zeros, right? There's no odd integers, if you will, in this output array. So in example 2, we have our input array digits to be 2, 2, 8, 8, 2. In this case, we have all of these different things. And notice how we can actually use 3 different 2's to still form a valid integer, because we have an occurrence or frequency of 3 for the number of 2's in the input array digits. Since we don't just have one unique 2, but we have 3 unique 2's, 2, 2, 2, using all 3 unique 2's would still be considered a valid integer to use, or a valid integer to use, right? So in example 3, we have the input array digits to be 3, 7, 5. We can't do anything here because, first of all, we can only form one kind of combination of 3 elements in 3, 7, 5. Sure, we can have 7, 5, 3, or 5, 7, 3, or 5, 3, 7, but no matter what we do, we're not going to form any even integers because every digit in the input array is odd, right? And again, one of the requirements that we need to have for the integers in our output is that they have to be even, and none of the digits have that property of being even in the input array, hence we have an empty list for our output. So for the constraints here, we see that the number of digits in the input array digits is going to be between 3 and 100. We're also given that digits at any index I is going to be between 0 and 9. Now, let's kind of logically try to approach this problem. We know that any integer that we're going to have in our output, it's going to guaranteed have a length of 3. Why? Because it's quite literally defined to be the concatenation of 3 different elements from the digits in any arbitrary order. And note, when I say different, I don't mean different in value, but rather different in indexing, right? They can be the same values, but they just have to be from different indices, like we saw in example 2. So, when we think about, okay, the integer has to be, any integer in our output has to be a length of 3, you get in your mind a specific range that any integer in the output has to be in. We know that any integer in our output is going to have to be any 3-digit integer. Now, every single 3-digit integer that exists, well, in the universe, it's going to be between or within a range from 100 to 999, right? Why? Because 100 to 999 covers all of the integers that have a length of 3, or that are 3, that are 3-digit, right? They're 3-digit integers. And so if we iterate over all the different elements from 100 to 900, we can then check if it's possible to form them from different elements from different indices in the input array, and increment our resulting list accordingly. So that's how we're going to solve this problem. That was the main observation to make, is that every single integer that we can potentially have in our output has to be within the range from 100 to 999, because that is the range that covers all the possible integers that are 3-digited, right? Meaning they have a length of 3, which is one of the properties of our output integers, right? So let's go ahead and begin coding up the solution here. The first thing that I'm going to do is, quite palpably initialize my result list. Sorry. this is effectively what I'm going to be returning. It's going to store the list of all the different numbers in that range that are 3-digited that actually do have that property and that we can form from our input array. Now, something that I'll quickly explain, we also do actually want the overall counter of our digits because we also do care about the frequency of all the different elements in our input array digits, as we saw again in example 2, because not only can we form 2, 2 and something else, we can also form 2, 2, 2 because we have that according frequency to use 3 different 2's to form a unique 3-digit integer. And so I'm going to get the count. I'll call it count. It's basically going to be the counter of the input array nums, or rather I should say digits, where every single integer, or rather, yeah, every single digit in the input array digits is going to be mapped to its corresponding frequency, right? So now let's actually begin our iteration in the range, in the valid range, if you will, of 3-digit numbers from the range from 100 and 1,000. And the way it's going to work in Python, actually, is going to be for every single number or integer in the range. We're going to, of course, start from 100. We're going to go up until 1,000 exclusive, meaning up until 999. And we also want to have a third parameter. In this case, the third parameter tells us how much we want to increment by in each iteration. And since we only care about all of the even integers in this range, we're going to increment by 2 in each iteration, right? Instead of going from 100 to 101, 202, 203, if we increment by 2, we're only going to cover the even integers in every single iteration in this range. We're going to go instead from 100 to 102, to 104, to 106, only covering all the even integers because those are the only type of integers that we actually care about in that range to be valid outputs, right? So from all the even numbers from 100 to technically 199, 100 to 998, not even 999 because 999 is actually odd. For every even number from 100 to technically 998, we're going to actually get its kind of digits in a form of a list to accurately get its frequency to check if we can actually form it based on the digits frequency, right? So look at the num of the digits. I'll just call it num digits. Basically, it's just the digits in a num list, if you will. And I'm going to be using something called list comprehension here. It's going to be basically a list of every integer d for every d in the string of num. And once I get the num digit, I'm going to then get the counter, the temporary counter, if you will, of this current integer in the form of a list, right? So I'm going to get the counter, or rather I'll call it temp count, because it's a temporary counter for this specific integer in this range or iteration. And it's going to be a counter of the list of the num digits, right? Now, to kind of quickly reiterate, assume in our iteration we were currently at 102. Our num digits, instead of being just 102 as an integer, it would instead look like 102. It'd basically just be a list with every single integer in the form of a list, right? Basically, we're adding the integer, we're adding every digit in the form of an integer in this integer num, in the form, or rather into a list, right? And we just go through the string of them to be able to actually append it to the list, right? Because we can't really iterate over an integer, we can only iterate over a string. That's why we convert it to a string, right? So that's just a quick example here. Once we get that, we then get the frequency or the count of all the digits in this current integer, because that'll help us determine if we can actually form it with the frequency of these digits in the input array digits to see if we can actually form it and add it to a result accordingly. So the way we can check that is using the all keyword in Python. If we know we have enough digits to form this number throughout every single digit in the input array digits for this every single digit in this current number, right? So if all, meaning if this applies for all cases, temp count at every single value, I'll just say d, if it's less than or equal to count at d for every d in temp count, we know that this is actually a valid integer or a valid kind of integer in this range, and so we can add it to our result, the current number num, and effectively return, once we actually iterate over all the integers from the range from 100 to 998 that are even, once the for loop executes, once the filing terminates, we'll just basically just return res, as it would actually store all the even integers that have the property that we can actually form from the input array digits that are all even, right? So to kind of quickly reiterate here, basically, for every single unique value in the current digit, right, and the current num, I should say, in this range, if its frequency is less than the frequency in our actual overall integer digits, we know we can actually form it, right? Because if we need, per se, 2 2's to be able to form this digit, if we have 2 or more 2's in the entire input array digits, we know we can form them because we know we have enough of that specific digit to actually form that specific digit in the input array num. And if that applies for all digits in the current integer, we know for all digits we have enough digits basically that have a frequency that is greater than or equal to the frequency of it in the current digit. We know it's greater and we can actually form it, right? Kind of taking to example 109. right? Assume 109 is, or rather 208. Or 288, I don't know, it doesn't really matter, right? Assume the current integer is 288, and our input array is this. In this case, the frequency of 2 for the current number is 1, and the frequency of 2 in the overall digits is 3. Since 3 is greater than 1, we know we have enough 2's in the overall input to actually form the number of 2's that we need for this digit. We know the frequency of 8 in this case is 2. Since the frequency of the overall digits is also 2, and 2 is greater than or equal to 2, we know we have enough 8's to form all the 8's needed to form this number as well. And so this is a valid number. We can actually form it giving the amount of digits we have in the entire input array digits to actually form this current number num, and it is valid, and so we append it to the result as one more valid number in the range that is even from 100 to 998, and effectively we return res that stores all the different actual values that are kind of valid, or integers that are valid in that range, if you will, right? So unless I made the syntax errors here, they should be accepted, there should be a valid solution, so let's go ahead and verify that. And as you can see, this really is just about as efficient as you can get it to be. So at a high level, basically to kind of reiterate, we're basically just going from every single value, all the different 3-digit numbers, we're getting its frequency of all the different digits we need. If the frequency of every single digit in the current number is less than or equal to the frequency that we overall have to be able to actually available to use in the entire input array digits, we know it's actually a valid integer, and we can append it to our result and return our res to basically just be the number of valid integers, or rather all the different valid integers in the range from 100 to 998, all that are even, that is. Right. So for the runtime complexity here, very straightforwardly, it's just linear, or rather, it's just big O of n, right? You could call it. Now, the key thing to note here is that we're actually going through a constant number of iterations, right? And give me a minute, guys. Sorry about that. Let me just quickly. Sorry about that, guys. Just had to fix a couple microphone issues here. Getting back to what I was saying. So, for the runtime complexity here, I did not mean big O of n. Sorry about that. You could call it big O of n, but realistically, we're iterating over a constant fixed amount range, if you will. We're always going to iterate over 100 to 998. Regardless of our input array, that's never going to change, and so it's going to be constant or big O of 1. Right? Technically, big O of 450, that's why I was trying to say big O of n, where n is basically just a constant big O of 450, but we know constants and coefficients and runtime complexities really don't matter, so it's just a simplified big O of 1, or constant runtime complexity, and for the memory or space complexity, it's going to be in big O of k, if you will. Right? K is nothing but basically the length of our counter, because we do actually get the counter of the digits, and so it's going to be basically just the number of unique digits in the input array digits, right? So if you guys enjoyed the solution and learned something new, please consider liking this video and subscribing to my channel. And without further ado, I will see you guys in the next video. Bye-bye.